We're going to talk about the phase estimation algorithm. So let's say we have a unitary U and we have an eigenvector of U, which is, let's say, ket U. And I have the eigenvector eigenvalue equation. So this is equal to some eigenvalue. I'll write it as e to the 2 pi I theta ket U. Now this is the eigenvector of U. And as you know that the eigenvalues of a unitary operator lie on the unit circle of the complex plane. So therefore, this is the eigenvector eigenvalue equation of a unitary operator, and theta lies between 0 and 1. So the phase estimation problem is to estimate theta given this unitary U and its eigenvector ket U. Okay, so we are going to do the phase estimation algorithm in step by steps. First, we are going to take a couple of simple cases in this video. So let's see. So theta is a real number. So it has, let's say, a bit representation. In the simple cases, we are going to assume, let's start with simple case 1. So simple case number 1 will be if theta is equal to just can be represented in just one bit. So, right. So that means that theta is either 0 or theta is 1 over 2. Right. So let's see if we can build the circuits if we know in advance that theta is as simple as this. Okay. So let me draw this circuit. So we have a top register. We have the Hadamard gate on the top. And then we have, so this is 0, ket 0. And this is ket U. So this will be the eigenvector which is fed into the bottom register. And then there will be a control gate. And this will be U. And then over here, again, we apply the Hadamard gate. And then finally, there is a measurement. Right. So let's analyze this circuit. So let's look at various points in the circuit. This is psi 0, psi 1, psi 2, psi 3. Right? So psi 0 is just ket 0 tensor ket U. Psi 1 is the Hadamard gate that gets applied on the top register. So this is ket 0 plus ket 1 over square root of 2 tensor U. Next, there is a control U gate, right? So let me write this before I do that. Let me write this as 0 tensor U plus 1 tensor U over square root of 2. Now, this is the control bit and this is the target bit. Similarly, this is the control bit and this is the target bit. So now when I apply the control U gate, if the control bit is not set, then nothing happens. If the control bit is set, then the unitary U gets applied to U. But this is an eigenvector of U, so this will be 0 tensor U plus e to the 2 pi I 0 point theta 1 tensor U. And this is because we are taking the simple case of theta being represented by just one bit. Now I can factor this. I can take this u out, and then I can write this as ket 0 plus e to the 2 pi I 0 point theta 1 ket 1 over square root of 2 tensor u. Okay, so notice what has happened is that there is a phase kickback that has happened from the target bit over to the control bit, right? So this is phase kickback. The control bit got changed over here due to this phase kickback phenomena that we have seen earlier. And now we have two cases. Theta 1 is equal to 0, then psi 2 is equal to ket 0 plus ket 1 over square root of 2 tensor u. And if theta 1 equal to 1, then 2 is equal to ket 0 minus ket 1 over square root of 2 tensor u. So therefore, if I apply the Hadamard gate and measure, then I'll exactly get the theta 1 as the answer. So when I measure, finally, I'll get over here theta 1, right? So applying the Hadamard gate converts it to, so psi 3 should be equal to ket 0 if theta 1 is equal to 0 and 1 if theta 1 is equal to 1. So that is after applying the Hadamard gate. Okay, so that is if theta 1 can be represented by just one bit. Now, simple case 2 is, let's say theta is equal to 0 point theta 1, theta 2. So maybe there is a 2-bit representation. So therefore, theta can be either 0 or half or 1/4, right? Or maybe it could be 3/4 as well, right? So these are the four possibilities of theta in this case. Now the circuit is similar. Now we'll have 2 bits on the top register for this 2-bit accuracy. Now this has to be known in advance, right? So we need to know that theta has 2 bits of accuracy. And then we have the Hadamard gate over here. Again, another Hadamard gate over here. This is 0, 0. And then the bottom, I have again this eigenvector u. And then I have the control u. And this is controlling again. But this will be u square. And then there will be I'll draw a box over here, which will fill in later. And then there's a sort of a measurement. Right, so that will be the circuit for this case. So let's analyze this again. So this will be psi 0, psi 1, draw this psi 2, psi 3, and psi 4. Okay, so psi 0 is just psi0 is equal to 0 tensor 0 tensor u. Psi1 is after applying the two Hadamard gates, this first qubit will be 0 plus 1 over square root of 2. Second also will be 0 plus 1 over square root of 2. And the third will remain in ket u. Now, the control U gate gets applied. So we've already looked at this situation before. So this is the control bit and this is the target bit, and the same thing will happen. The phase of the target bit gets transferred over to the control bit in a phenomena called the phase kickback. So this psi2 will be equal to ket 0 plus e to the 2 pi I 0 point theta 1 theta 2 ket 1 over square root of 2. And then that is happens after the first control U gate gets applied. Now control U square gate gets applied with the target control bit being the first qubit and the target bit being the third qubit, right? So what happens over there? So now the phase that gets kicked back is not this, because if I take U applied to U is equal to e to the 2 pi I theta 0 point theta 1 theta 2 0 point theta 1 theta 2 ket u. If I apply u again, u square of u, this will be u applied to e to the 2 pi I 0 point theta 1 theta 2 u, which is equal to e to the 2 pi I theta 1 theta 2 0 point, sorry. U applied to u, which will be equal to e to the 2 pi I 0 point theta 1 theta 2 square u, right? So this will be e to the 2 pi I 2 times 0 point theta 1 theta 2 u. But this is a binary representation, so this will just move the decimal point 1 to the right. So this will be e to the 2 pi I theta 1 point theta 2 u. But this is equal to e to the 2 pi I 0 point theta 2 u, because e to the pi I theta 1 is just 1, whether theta 1 is 0 or 1. So you'll get this. So this is the phase that gets transferred up when you have the control U square gate, right? So therefore psi3, so we have this psi2 over here. So psi3 will be at 0 plus e to the 2 pi I. Okay, I made a slight mistake over here. This thing, it should not be over here. This is the second qubit, right? So I should erase this. So this is ket 1 tensor ket 0 plus e to the 2 pi I 0 point theta 1 theta 2 1 square root of 2, right? So this is because the control U gate is on the second qubit, whereas the control U square gate is on the first qubit. So now when the phase gets transferred from the control U square operation, this will be 0 point theta 2 ket 1 tensor 0 plus e to the 2 pi I 0 point theta 1 theta 2 ket 1 over square root of 2. tensor U. Now this looks familiar. This is actually, we have studied before. This is the QFT of theta 1, theta 2. So taking the QFT inverse after this should give us this result, right? And which is what we want. So this box over here is actually QFT inverse, and this will be a 4-dimensional QFT or 2 raised to 2-dimensional QFT. So this will give us theta 1, theta 2, and then when we measure, we'll get the classical values, right? So this is the simple cases of the phase estimation algorithm.